First of all, let me thank Anna Scaglione for being so kind to give this keynote speech. It's very nice to have her with us today. So let me introduce her properly. Anna Scaglione is a professor of electrical, computer, and energy engineering at Arizona State University. Previously, Anna was at the University of California at Davis, at Cornell University, and at the University of New Mexico. Anna's expertise is in the area of statistical signal processing with application to communication networks, electric power systems, intelligent infrastructure, and network science. She is IEEE Fellow. She is the recipient of several awards, among which let me mention the IEEE Signal Processing Transactions Best Paper Award that she got in year 2000, and the 2020 Technical Achievement Award from the IEEE Communication Society on Smart Grid Communications. So it's my great pleasure to welcome Anna to this conference. The title of her talk today is Grid Graph Signal Processing, Theory and Practical Applications. So Anna, the floor is yours.
Thank you so much, Miguel, and thank you for having me. It's such a pleasure. I want to announce to everybody I'm going to go back to Cornell in fall. So I'm going to be at Cornell Tech in New York City. So my step moving around is hopefully going to stop. Okay, so I want to acknowledge my former student Rakshara Ramakrishna and Hoito Wai for the work that I'm going to talk about. So a lot of people right now are interested in applying machine learning and artificial intelligence to the grid. And one of the primitives, one of the models that is used frequently in machine learning is the model of a graph. It's using statistics when we try to model the statistical association of several data sets through the notion of conditional independence in Bayesian networks. It is also used to represent the underlying topology, low-dimensional topology of data that are embedded in high-dimensional spaces for clustering and for other machine learning primitives. And right now, there is a new area, relatively new area. It has been around for about 10 years, but it's been peaking over the last few years, which is called graph signal processing. And what graph signal processing attempts to do is to essentially extend the notion of discrete digital signal processing to data that are indexed by an irregular support. And it is based on the deterministic association of data set through an input-output relationship that allows to formalize the notion of filtering. So the electrical grid is a well-studied infrastructure network that has very specific physical laws that are derived from circuit theory. And in this case, the graph is represented by the transmission and distribution network, so by the electrical wiring. And the nodes are referred to as buses, and the edges are essentially the transmission lines. And the starting point here is that electrical grid signals are obviously indexed by such graphs. They can be bus measurements or line measurements. Graph theory concepts are obviously not new in power systems because the physical equations depend on the system matrix, which has the same sparsity of the graph. So there is a recent survey that covers all the graph classic methods in power systems to analyze both spatially as well as the temporal dynamics that I encourage everybody to read this by Isiak in 2018. Now, the use of Bayesian graphical model is another emerging area in the machine learning applied to power system. And this has been utilized for state estimation, topology estimation, and optimal power flow. Now, the question that I want to address in this talk is if we cast electric grid signal models in this graph signal processing, or for short, GSP framework, can we leapfrog all the evolutionary progress of grid data science and utilize this notion of filtering as a powerful feature extraction method? So I have to make a premise, obviously, on graph signal processing to just set the stage for what I'm going to say about grid signals. So as I mentioned, graph signals are signals or data that are indexed by the support, the regular support of a graph. So they have an associated graph G, where V is the set of nodes and E is the set of edges. And they also have an associated adjacency matrix, which has the same sparsity of the graph. So you will have a vector X in Rn, where n is the number of nodes, and essentially each index for each entry is a particular node in the graph. And where is the inspiration of generalizing the idea of this DSP? Effectively, one can interpret this DSP as providing signals that are indexed by a very simple graph. Most of DSP is based on looking at finite signal and the periodic repetition of finite signal that can be associated to the circular graph. And the adjacency matrix has this very simple circulant structure, which essentially is the geometric or the algebraic representation of what we call typically the shift operator, or in the Z domain would be Z to the -1. So the shift operator is what we want to generalize in graph signal processing. And we do that by, in the first papers that appeared on this topic, by essentially setting the GSO, which I will refer to as S, the graph shift operator, as the adjacency matrix that I showed here for the cyclic graph. And that in general would be the adjacency matrix for the graph, the regular graph that we choose. But more recently, after this first introduction, algebraic introduction to GSP, people have preferred an alternative to the actual shift operator. Unfortunately, they retained the name. And the shift operator now is typically the Laplacian operator, which can be obviously defined as a function of the adjacency matrix, as I show in this equation. And the graph Laplacian is not truly a shift, but rather a differentiator operator. So it can be compared more closely to the variable S in the Laplace transform. So what is a graph filter? Well, in algebraic terms, it's simply a multiplication by an operator, H, that is a function of S. This is what we call the input-output relationship, even though, unlike the case of causal filter, it really doesn't necessarily imply that we are saying that W is the cause of X. It is simply a representation that, as I said, helps generalizing filtering operation to these kind of signals. And what we want for this operator is to have the so-called shift invariance property that dictates that multiply from the left side or from the right side, this filter, this graph filter by the shift operator provides the same exact matrix. So if you shift the input, you obtain essentially the shifted output as shown in this equation. Now, this constraint, the constraint of being shift invariant, implies that the class of graph filter has to be a matrix polynomial, possibly of infinite order. And here I'm giving a couple of examples of legitimate graph filters. These would correspond to essentially a geometric series here, and this other filter is a matrix exponential. Now that we have set up the basic functions, so what is the graph shift operator, the GSO, and what is a graph filter, then we want to generalize, as I said, the notion of the premier notion of DSP, which is that of filtering, and in particular, the discrete time Fourier transform. And for the cyclic graph, not surprisingly, the eigenvectors of the GSO are in fact the DFT, the well-known discrete Fourier transform. So the natural generalization is to take as GFT the eigenvectors of the general GSO that is defined over a graph which has an irregular support in general. And so X tilde will be simply the multiplication of the inverse of the U matrix, that is the eigenvalue decomposition of the GSO, times the graph signal x. Now, the transfer function is defined, obviously, taking the Fourier transform from the right and left side of the graph shift operator. And since the GFT diagonalizes every term in the matrix polynomial, clearly the transfer function is going to be a diagonal operator, where H tilde is nothing but the matrix polynomial defined here in this equation, where each entry of these the diagonal entries of the full transfer function is essentially a matrix polynomial, where the polynomial is in the eigenvalue of the GSO. And this allows to recover the well-known relationship that we have in DSP, where in the frequency domain, the input-output relationship is an entry-by-entry multiplication of the input by the transfer function, as shown here. Now we assume that the eigenvalues are ordered in increasing order. And for a graph Laplacian, the smallest eigenvalue is always 0, and the smallest eigenvector is always a constant. Now we have defined frequencies. An important concept in DSP is that frequencies have an ordering based on the variation that they have, right? So we have a high frequency, which is varying faster, and a low frequency, which is varying slower. And the constant signal, obviously, is the lowest frequency, is frequency 0. So how do we generalize this idea? Well, we can utilize the concept of total variation, which is the norm of the signal after we apply the GSO operator, which again, in this case, is a Laplacian, and so it corresponds to sort of taking the spatial derivative of the signal. And the lowest is the variation, right? The lowest is the derivative of this signal, the smoother the signal is over the support. And so since we said that the GFT basis is formed by the eigenvectors of the GSO, each of the GSO eigenvectors will have, after premultiplication by S, a norm which is scaled by the corresponding eigenvalue to the p power, if this is the p norm. So that means if lambda is small, the variation is small, and if lambda is large, the variation is large. And therefore, this ordering of the eigenvalues is a natural ordering for the graph frequencies. And in fact, typically, is best to index the graph filter spectrum, the graph signal spectrum by the eigenvalues themselves. As I said, for the smallest eigenvalue, which is 0, the eigenvector is a constant, which is the smoothest possible signal on the graph. And as you grow the eigenvalues, we can see emerging first the essentially the community structure of the graph, as you can see here, where the nodes are divided by red and blue color, based essentially on the entries, on the intensity of the entries over the eigenvectors. And as we grow in graph frequency or in the magnitude of the eigenvalue, you can see that the signal increases its variation. So the graph frequencies, as I said, are going to be the eigenvalues ordered in increasing order. So for applying this concept to grid signals, the first step is to generalize the theory to complex value graph signals. And in this case, the graph shift operator also has to be complex. Now, while in certain applications it possibly can be a Hermitian operator, we will see that that's not the case for grid signals. It's going to be a symmetric operator, but not Hermitian. Nonetheless, a symmetric complex matrix can be diagonalized through a complex orthogonal operator. And in this case, the eigenvalue decomposition has an inverse, which is the transpose. It will be the Hermitian if S was an Hermitian matrix. And these are orthogonal in the sense that U transpose U and U transpose provide an identity matrix. But it's noticeable that U is not the inverse of the U matrix. So if you multiply U inverse by U, you don't get the identity matrix. So at this point, what we propose is to utilize essentially as a graph Fourier transform the basis U, this orthogonal basis. And the frequency ordering in this case has to be based again on the variation. We see the variation is a function of the absolute value to the p power of the eigenvalue. So there is no difficulty here. We just simply have to take the absolute value of these complex eigenvalues for this orthogonal matrix diagonalization. How do we combine this with the idea that certainly in grid graph signals, but in general, we often have time series, right? So signals that are not static over a certain set of nodes, but you have several samples in time. Now, in this case, the generalization is actually quite simple. All you have to do is to use as a GSO, essentially the one that is defined over the product graph, where the GSO for the cyclic graph is nothing but the Laplacian for this derives through the shift adjacency matrix. And the overall GSO can be obtained by this formula, where this represents the Kronecker product. And because of this structure, then the GFT will be the Kronecker product of the respective GFT that diagonalize the spatial and the temporal operator. And obviously you can define, in this case, a combined filtering operation of graph temporal filter. These are not always decomposable in the product of two filters, unfortunately. So the most general structure would be for a finite order filter would be as follows. They don't have to be finite order, they can be infinite order. And the corresponding operation would be a convolution with all of these matrix polynomials. And of course, here in this case, when you take the GFT or the Z transform in space and time, you obtain, you can first take the GFT with respect to the graph, and then take the Z transform or Fourier transform with respect to the time index, and obtain, again, a multiplication on an entry by entry basis with the spatial and temporal GFT of the filter. And one particular case of these filters that I will use in this talk is the generalization of the autoregressing moving average model for graph filters, where here this is the conventional operation where you have a feedback component. These are A1 and AQ are matrix polynomials, and so are B, which are the B matrices that correspond to the MA components. And obviously in the combined Fourier and Z domain, you get this entry by entry multiplication by these transfer function A and B, which are also themselves polynomials in the eigenvalues of the GSO. Now, one property that is found often, not just in power systems, as I will argue, but also in other dynamical models, like models for opinion dynamics in social networks, or model for interaction in financial networks, that in general are diffusion processes, is that this graph signal tends to be low pass. In other words, the graph signal, if you take the GFT, tend to be concentrated in the low frequency components. And this actually causes this interesting property that you not only tend to have low rank signals if you collect many samples, but you also tend to have low rank signals that are concentrated in the smallest eigenvectors of the GSO. And this is an interesting connection with a lot of papers that observe empirically that measurement in the grid tend to have these low rank properties. However, they didn't essentially found this connection between these low pass properties and the fact that this principal subspace is actually tied to the system matrix. So now that I have made this premise, I want to also obviously move on to the topic of this talk, which is grid graph signal processing. And the first step, as I said, is to establish what is the appropriate graph shift operator. And in this case, not surprisingly, is essentially based on the system admittance matrix of the graph, which is a form of complex graph Laplacian. And as I said in my previous part, it is symmetric, but it is not Hermitian. In my talk, it will be convenient to partition the network in the section which has the connections among generators, which will be this block that I represent in blue, the section that contains only load, and these connections which are in the off-diagonal blocks. And the signal that I'm going to focus on is the voltage phasor measurements, which also are trying to capture essentially as measurements of the state of the system. Now, what is the starting point to define the GSO is essentially Ohm's law. Ohm's law is defined not only as a function of the system matrix, but there is also a diagonal term which essentially is tied to the losses of the system. And this diagonal term contains what are called the shunt admittances. And again, I am dividing them between shunt admittances of generators and shunt admittances of load. Similarly, I divide the voltage vector in the voltages of the generators and the voltages of the load, as well as the current of the generator and current of the load. And this partition is useful also to understand the connections with the dynamics of generators that are typically represented in terms of a vector of internal voltages, which I refer to as ET. And the relationship between the generator currents, the generator voltages, and the internal voltages is also through an equivalent circuit that has its own impedances, its own admittances, YG. And so you can see it in equation 16. So it is convenient, once again, to understand the dynamics and connect them, temporal dynamics, and connect them to the dynamics of generators, to now include the internal generator admittances in the top term of this diagonal matrix and simplify the equation so they are expressed directly in terms of the generator internal voltages and load currents. And so once we have that, then what is our graph filter model? We say that the voltages are a graph filter multiplied by this excitation, and this eta t is essentially a modeling error, where the filter is nothing but the inverse of the matrix that I just defined. And so the operator S is the appropriate graph shift operator. And what is S to the -1? Just like in a Laplace transform, 1 over S represents an integrator equation. This is also true for this filter, right? And so as I mentioned, an integrator is a low-pass filter. The frequency response is actually quite simple, is given by the reciprocal of the eigenvectors of the GSO. And as I mentioned before, the GFT is nothing but the eigenvectors of the graph shift operator. And this is what explains the low rank nature of the voltage phasor signals. Here I have a sequence of voltage phasors from a synthetic grid, which is the actives 2000 bus cases, which emulate the parameters and dynamics of the Texas network. This is actually a project. This is a result of a project from ARPA-E that I was involved with. And you can see that there is this distinctive drop as 1 over L. Here it's indexed by the graph frequencies, which are normalized. And so the spectrum decreases rapidly, and that justifies the fact that the voltage phasors generally can be expressed as a linear combination of the low-pass graph frequencies only as an approximation. So the other interesting aspect is that if you decimate a graph signal, then you still have a graph signal. And in particular, your operator will be expressed as a reduction of the original signal. So this calligraphic M is nothing but a set of measurements that you have. The corresponding GSO is obtained by taking the block of the matrix that correspond to the measurements you have available and subtracting this term. And the excitation here is represented as follows. And also in this case, this is a low pass graph filter, and this is verified here, taking 167 measurements out of the previous case of the active case that has 2000 buses. And here I take 261 measurements, and you can see that the spectrum in red is also low pass. The other notable fact is that as you restrict the number of measurements, the frequency content increases because this eventual reduction actually provides a sparser network and a denser network, and that yields more significant spectral component at higher graph frequencies. So now let's go to the dynamics, the temporal dynamics. So here it's important to connect these temporal dynamics to the actual physical equation that are utilized in power systems to justify the transient dynamics of the network. And the basic equations are the so-called swing equations, which I'm showing in equation 17. Now, these equations are equations that tie the angle of the internal generator buses to the imbalance between the mechanical power of the rotor and the electrical power which is extracted by the generator bus to feed essentially the rest of the network. And these are second order equations because the swing equation tie the derivative of the frequency to this imbalance, and the frequency is obviously the derivative of the phase. And these equations can produce oscillations, and these oscillations are quite disconcerting when the swing is fairly high, because obviously in this case the rotor becomes disengaged by protective system and can cause cascading failure. So it's very important to essentially detect these dynamics and understand what will be the impact on the grid itself. Now, to understand what are the modes for this system, it's important also to make this following simplification, which utilize the model of constant impedance loads. In other words, it assumes that the ratio between the apparent power and the voltage magnitude at a load bus is constant over the period where these dynamics are observed. And with this constant impedance model, what we can do is we can essentially move these admittance again in the GSO and set to 0, since they are dependent on only the generator buses, the portion of the voltages that correspond to the portion of the current of the load that correspond to the excitation. And so with that, we have set up the spatial model with 19. Let's go back to the temporal model. The temporal model, as we said, is based on modeling the dynamics of the phase of the signal. So what we can do is essentially acknowledging this by taking a nonlinear transformation of the signal, is simply a logarithm. And this logarithm imaginary part would be no other than the phase. For the representation, it's also important to rescale the logarithm of the generator dynamics by this vector M that contains the masses of the dynamics. And if that is done, what we can do is we can define this matrix where this block SCI correspond only to the connections between the load buses. And because this part of the excitation is zeroed out by bringing the constant admittance to the other one, what we can do is express the relationship between the generator through what is called the Cron reduction of this matrix, taking the Schur complement of the block SCI with respect to the matrix that we just defined, 21. And this essentially defines an all-generator network, where this all-generator network is, as I said, a function of the Coulomb reduction, and these masses that I use here to rescale the signal can be essentially taken out here by utilizing this rescaling factor that essentially removes that effect. And that is important to simplify the model for the dynamics, which become a graph AR2 model for the angle, and we generalize that to also the amplitude. Essentially the fact that this second order comes from the second order differential equation of the swing dynamics. So this block diagram is quite busy, but it summarizes most of the modeling. The modeling of the spatial graph filter derived from Ohm's law, which is an integrator in this, is over here. And aside from these rescaling component, the generator dynamics are captured in this blue block. And this is just the image of the relationship of a graph filter of second order, AR second order in the graph Fourier domain, where the graph frequency in this case are the graph frequencies of the all generator network obtained with the Coulomb reduction for getting the GSO. For the load current dynamic, has been proposed in the literature to also use an AR2 model. These, again, just like the dynamics of the amplitude, are empirical models, so it requires some validation. So on the top, we have modeled the GFT of the logarithm of the generator only passes. This is an absolute value. You can see in this case that the decay of the graph frequency spectrum is lower, even though the effect is also that of an integrator. And the reason for that is that in general, after Coulomb reduction, this GSO is actually quite dense. This is what you get as a spectrum in the graph Fourier domain and in the omega domain. You can see that also this AR filter is relatively low pass, but at the lowest graph frequency, there is more spread in the frequency spectrum. And then here we just simply verified that we could track the signal, the current and real and imaginary part, and the graph signal, real and imaginary part through this AR model. So once we have established that this GSP model is true, why can we leapfrog several steps that are normally necessary to provide the analytical tools or algorithms for grid signals? Because GSP has developed a set of tools, as I said, from taking inspiration from DSP. And therefore, this becomes essentially low-hanging fruit. You can apply these techniques to graph signals. And the low-hanging fruit is, the first low-hanging fruit is the notion of sampling and reconstruction of grid graph signals. But then you can add to that network inference, which is now not based on Bayesian graphical models, but rather on this physical model. And then that is actually richer because you can actually utilize Ohm's law to regularize your problem. And then you can solve other problems like interpolation of missing sample, but also importantly, anomaly detection. And this is just a start. These are kind of straightforward generalizations that we can apply. So as far as sampling theorem is concerned, what sampling does is decimate the original graph signal over the complete support, taking, again, a subset of measurements. And the underlying assumption is that the components that dominate in these graph signals are a certain set of K of frequency components that for the grid we saw is essentially the low pass components. And so what is essentially assumed is that if you use a projector operator for the signal that you are decimating, in this case the voltage, then you get an approximation of the original signal, which is actually quite good. So basically what this operator does is a band limited operator. It's sort of like an anti-aliasing filter that blocks every other component but the ones that are in the support K. And again, if your signal was concentrated already in that particular subspace, this is a good approximation of the original signal. The sampling operator or vertex limiting operator is simply a selection matrix that here is represented by this operator P transpose. P transpose is a fat matrix, and you can also define a projector over this operator. And essentially the reconstruction formula that you obtain is that once you have decimated the signal, since you know that V of t originally is in a low dimensional space, you can use the combination of these notions to obtain an approximation that essentially leverages this equation up here. And what you want is for this combination of the projection operator and the subspace UK to be a nicely conditioned matrix in order to get the best possible approximation that you can, which is obviously now also a function of what measurement you took. And so not only you want this to be low rank, but you want it to be well conditioned. So one criterion to select your optimum set is to maximize the smaller singular value of this operator D multiplied by UK. And this is a sampling scheme that was proposed in 2016 in general for graph signal. And as I said, you can leapfrog this result, the derivation of an optimum placement for voltage phasors and therefore phasor measurement units from this theory. And what do you get? So as I said, this is a low pass signal. So what makes actually this matrix well conditioned, what minimizes, has a nice interpretation. This is a SPI diagram of the active cases I was working with before. And you can see that it has a clear community structure. That's not surprising because obviously the most densely connected areas are cities in Texas. And then they are sparsely connected among each other, and generators tend to be connected to certain areas serving the system. So this connection between generator buses up here and the rest of the communities is almost diagonal with few exceptions. So here I'm showing you the Misco error performance versus the number of samples. Where we didn't exactly solve the minimization because it's a combinatorial problem with respect to the placement, but we utilize a greedy approach to place the measurements. And as I said, because of this community structure, then the eigenvectors will tend to essentially, the various frequencies will tend to be concentrated, have a smooth structure in all of these communities, as I showed previously about trying to interpret graph frequencies. And so what happens is you tend to place sensors so that they cover essentially every community well. And the results are, amazingly good. You have 2,000 buses, and you can see that you go below 1% of error with only 200. So it's an order of magnitude fewer samples than necessary. Then consider necessary to have observability, which typically is 50%, so 1,000 samples. Now, we can also estimate the GSO that will give us information on the system metrics. And compared to methods that use graphical models, what we are trying to do is not just simply utilize correlation and utilize methods such as graphical lasso that use sparsity in the covariance metrics, but we can use actually explicitly Ohm's law and regularize the system by essentially utilizing the fact that we have a sparse graph. This will be this term. But also most importantly, what we know is that the S is a differentiator operator. So what we want to minimize is the total variation. And here we have T samples of the graph signals. And then we have to impose obviously constraints on S, which are symmetry, and also the fact that we know from power systems that the imaginary part of the S matrix tends to dominate. So we want to force the traces of these signals to be in the order of what is known as essentially the relation between the imaginary part, there's a acceptance, and the real part, which is the conductance of the system. In this case, we actually applied this network inference problem to real data from the New England independent system operator. Here is the diagram that is given along with this set of data that were collected after there was a generator failure. And you can see here that the connections among these PMUs are provided explicitly, sorry, among these generators that are, whose phases are measured as provided explicitly. And our graph inference by diagram captures actually the connections that are acknowledged in this set of data. Now, if you can utilize a fixed pattern for sampling, which is a decimation of the original signal, it's not surprising that you can also interpolate signals that are missing due to failures of the communication or the fact that they are essentially outliers. So in this case, we focus on the fact that the measurements are missing, but it's actually not difficult to generalize this case where you have outliers. And so what is the point? Like the point is that you have over a certain support available measurement. This is a matrix of measurement you've taken over time, and you're trying to make an interpolation of this matrix, which is incomplete, by essentially trying to minimize the mean squared error between the measurements you have and your regression over V. And then you can include the other terms that we said. So you want that with respect to the GSO, that in this case, in this regression problem, you want to have total variation, which is small. But also we know that these signals are an AR2 model. So we also want temporal variation, which is small, which is this other term. And these are this regularization term. And this idea of interpolating samples, the need of interpolating samples has been addressed by other papers. This is one of the first papers in 2018 by Zhang et al. That has covered this. And the typical approach is to utilize matrix completion, which doesn't essentially leverage an explicit total variation, but it simply assumes that the measurements have to be low rank in space and have small total variation in time. And so since this is the benchmark, we compared ourselves against this method. So here is the original set of PMU measurements. Again, this is the New England ISO. We corrupted these measurements as follows. You see the blank areas is where you are missing signals. And in some cases, you are missing entire segment of these signals. And this is where essentially our method shines, simply because we acknowledge that we know the eigenvectors of the principal eigenvectors of the voltage measurements. We know that they are concentrated in the low pass graph frequency components utilizing the appropriate GSO. And so that's why our reconstruction performance are better than the method I mentioned before. This is the acronym used in the paper. And we have 50% of missing samples. And as you can see, we perform quite well. So we can also utilize the fact that we have spatial and temporal dynamic to compress the measurements. So not only we can sample, but we can also compress utilizing the fact that we know that there is essentially a graph filter AR2 model, which essentially allows for a differential type of scheme for compression. And this tilde hat is your representation, compressed representation of the signal, where you can utilize it to essentially track what should be the next signal based on what you have observed so far, and then essentially communicate only the residual with respect to this predictable component. So this will be the differential scheme that we use. At the encoding side, we essentially encode in the spectrum, the graph spectrum of the residual with respect to what is the prediction. And In the decoding side, we receive these encoded residual and we correct our state update. And the performance are actually pretty great. So the black line is the scalar quantization case, and this is the distortion versus the rate, the number of bits per sample that are utilized. Our method is the blue curve, and the red method is a batch method, which is based on singular value thresholding. So it takes a matrix of measurements and it extracts the principal eigenvectors and it then encodes only the most significant coefficient. And I would say this is not an apple-to-apple comparison because ours is a sequential scheme. So that has this distinct advantage that you can utilize it not only to store with fewer memory, but also to transmit at a lower rate. So let's go to the data injection attack problem. So the voltage current Ohm's law relationship is a linear relationship. But let's start defining in general a linear cyberphysical system equations are expressed as in equation 30, where we have Z, which is the output of some system matrix plus noise. And in general, the goal is to recover X based on knowledge of H, assuming that W can have outliers. And this regression is typically formulated as a least square problem or as a weighted least square problem. Now, one of the popular topics in power system security is that of circumventing a stealth attack to an outlier detection, where the attacker can actually manipulate a subset of the measurements and perturb them in such a way that this perturbation produces a change that depends on the particular rows of the system matrix that are multiplying delta X. But it's such that the remaining measurements, which are the honest nodes measurements, have an eigenvalue which is 0 exactly along the direction of this perturbation. And so if we have PMU measurement, Z is the combination of the available current and voltage measurements. And the relationship, the linear relationship H is represented by this matrix. Y is again the admittance matrix. This is the connection between the unavailable and available measurements. And what we're trying to do is essentially perform a regression on all the voltage phasor for available and unavailable measurements. And the stealth attack takes the form of a vector that is 0, obviously, on whatever are the unavailable and honest nodes measurements, and instead over the maliciously attacked measurements has a perturbation in the voltage measurements. It is such that it projects to the null space of this matrix YHM that I mentioned before. So what is the GSP angle of counterattack? The fact that we actually know the relationship between, we know that this relationship is a low pass relationship. And so what we know is that there is a graph filter through which the perturbation of measurements should be designed. So in other words, this delta V cannot be arbitrary. This delta V, in order to be a legitimate signal, has to have the structure that I'm showing here. And so the attacker would have, in fact, to place a perturbation delta E, which is in the null space, not of YHM, which is a fat matrix, but in fact, a combination of the graph filter, which is low pass, low rank, and this matrix. And what this does essentially regularizes the problem and makes it essentially impossible to satisfy this, because the combination of these two matrices tends to be full rank. And the detection technique doesn't even have to leverage the knowledge of this graph filter. It could, but it doesn't have to, because essentially what happens is that in the presence of an attack that doesn't follow this model, the signal becomes inappropriately a high pass graph signal. So what one can utilize is to either utilize explicitly this or just simply look at the high frequency components and essentially calculate what is the energy of the signal outside the appropriate subspace, and provide an hypothesis test that compares this energy with respect to a threshold tau. And if there is a lot of energy outside the appropriate subspace, the attack is detected. Otherwise, it's situation normal. And so here is the ROC curve for our method. The proposed method here is in black. There is a competing method here that I'm showing in red. And you can see that even if we have only 20% of the measurement, our receiver operating characteristic, which is showing probability of detection versus probability of false alarm, is excellent. And with 50% of the methods, we have nearly 100% detection in this case. And we can also isolate what are the suspected nodes. This is more difficult, but essentially what we are trying to do is to find a sparse support of this perturbation, because the attacker, as I said, has only a subset of measurement to perturb. And this can be formulated as, again, a projection. The fact that the projection over this orthogonal subspace has to be small, subject to the sparsity constraint, which is essentially providing a certain Byzantine fault tolerance. So we assume that the measurement set that is attacked is smaller than roughly mu. Times a scaling for the voltages, which is known, because essentially all these measurements are rescaled to be per unit. And so with this, I'm showing here both the projection over the subspace during an FTI attack. You can see that the blue components are very high, while this is essentially all zero during when the attack is not present. And here is the reconstruction for the elements that are attacked. And you can see that the actual positions are very similar to most of the entries that are estimated through 38, although there are, this is a more difficult problem, obviously, and we have some entries that are not identified. So I want to conclude at this point. So what I am essentially trying to attempt is not to change the laws of physics. I'm utilizing the grid laws of physics. But what I'm saying is that since graph signal processing is an expanding data science toolbox, particularly at this moment, essentially what we can do is to utilize the model that I propose to translate these GSP algorithms into algorithms that can be applied to grid signals. And what I've done is essentially taking the low-hanging fruit, and I want to take a little bit more of that low-hanging fruit. In particular, I want to deal with measurements other than voltage phasor measurements, which are expensive, particularly applying this modeling to apparent power, voltage and current magnitude, and modify my algorithms to deal with that. This is very important for distribution networks where the advanced metering infrastructure tends to measure apparent power and voltage magnitude, but not voltage phasors. But then what I really am interested in is utilizing essentially graph signal processing as a feature extraction to automate feature extractions. And in particular, we know the importance of convolutional neural networks for the analysis of images, or recursive neural networks for the analysis of time series through neural networks, where the feature extractions occurs at the first layers of the network. And the idea of graph signal processing is already applied to define graph convolutional neural networks. So in this case, we could essentially almost directly extend the theory and the modeling of graph, neural network, and the combination of that with the recurrent neural network to graph signals. Now, of course, one of the main issues is that there is a real scarcity of labeled data for the grid. But the possible solution is essentially using a digital twin of the system, simulate many realistic samples of failures or other type of situations that are anomalous and can evolve in a negative way for the system, and then train our neural network models on that. And with that, I conclude my talk. Most of the results that I've showed are in this paper that appeared on the transaction of signal processing in 2021. And then stay tuned for other results. I have already seen that there are a couple of citations to this paper, so it seems that it's going to be an expanding topic.
So Anna, thanks a lot for your very nice talk, very informative, very interesting. And it's really a good way to finish the first day on the first mirror and to start the first day on the second mirror. So I think we have time for some questions or comment from the audience. And so let me remind you that you can either use the chat or simply raise your hand and switch on the mic. I think I see a raised hand. Yes, from Omid. Yeah, sorry, Omid, I could not see it. Please go ahead.
Hi, Anna. Thanks for the very nice talk. So this is a problem that I'm very interested in, and I've been trying to apply these results to the distribution network. So I was trying to understand if there are fundamental differences when graph signal processing is applied to the transmission network and distribution network. And can we say that, for example, sparsity properties are different, or maybe the lower rank problem that we have is completely different, and anything on that could provide some insight on this. Yeah.
Yeah, as I said, this is low-hanging fruit. So in fact, I'm working on it. I just submitted the paper that talks about distribution network. Obviously, you have to acknowledge that it is a three-phase model, but so it's going to become a kind of a block matrix. And but the same properties are found in distribution network. It's a radial network and it's sparse, but it has the same exact properties, low rank. So you can take exactly the three-phase system matrix and define the GSO exactly according to this model, and you will find the same exact properties. The emphasis in that case, in my view, should be towards measurements that are not phasor measurement units, not because there are not phasor measurement units for the distribution grid. There are. However, they are quite expensive, and so but you can obviously indirectly utilize what you know about the low-pass nature of the voltage phasor and essentially relate the voltage phasors to the apparent power and to the voltage magnitude, and utilize that, the fact that you know the GSO as providing a low-dimensional representation also of these measurements, which is eventually related with the GFT of the voltage phasor itself. So it's a lower dimensional description that can be utilized for state estimation, for anomaly detection, for you name it, right? So it's important that once you know that the voltage phasors are represented in this fashion, you can utilize indirectly all of these expressions to make them formulate your problem in terms of other advanced middle infrastructure measurements. But definitely it can be applied. I can confirm. I have the curves, and you know, I just submitted the paper, so I didn't want to talk too much about it. But it's a new direction, which is very important, because right now distribution networks are even more important, I would say, than classical transmission networks.
Thanks, Anna. I also have like a question. Can you comment on the complexity of the approach and in terms of computation and storage, and these in particular with respect to scalability? Because if the complexity is large, then you might have problems of scalability.
Right. So, first of all, let's acknowledge that transmission power systems and also some distribution systems are very large, right? So the idea here is that, number one, even if you decimate the signal, right, you have also a low pass signal. So some of the processing, some of the anomaly detection, both for practical purposes, because you may not observe the whole phasors, right, or may not be able to do a complete regression, but also for the point of view of reconstructing what you're missing, they can be based on a decimated vector. But the main point of this analysis is also to acknowledge that there is a low dimensional structure that is known in the signal. This is something that has been used. People say, let's do PCA of the voltage covariance and utilize the particular principal component. But what I'm saying here is that you know what they are. They are the low pass graph frequencies. And so anything that relies on dimensionality reduction to reduce the complexity applies here. And so I think that's the best property, and also the fact that if you decimate, you have a similar structure that allows you to do a feature extraction through filtering without graph filtering, without necessarily having to deal with a very large, 70,000 bus measurements for the American system, which is quite intractable.
Are there other questions or comments? Well, I have also another curiosity, Anna, if I may. So you were talking about this false data injection, which of course is very important given how critical these infrastructures are and the importance they have also for security and safety. I was wondering, do you think it would be possible to, say, inject false signals which are similar to noise, so that you, say, sort of hide your false data as a noise that overlaps to your signal?
So if it is regular noise, what an outlier detector would detect it. So basically saying, okay, there is a least square mismatch between what I measure and what the model tells me that I have made a regression on. And so those are not stealth attacks. So the type of attack they measure is more sophisticated, assumes that the malicious attacker actually knows the system metrics and tricks this outlier detector, because there is no bad mismatch between what you have and what you measure for given the perturbation. But what I'm saying here is that that type of approach doesn't acknowledge the fact that the signal is low pass and is over a certain very specific graph filter. So if you have that knowledge, that particular operator that you try to hide your signal under by saying, I select my perturbation in the null space of this operator, doesn't have a null space. If you look at it as the cascade of a graph filter and an excitation, that becomes a full rank operator. So that is what you're using. You're essentially using further structure to say, not only you don't look like noise, but you don't look like a legitimate signal, because I know my signal have this additional structure that essentially makes it impossible, unless you have almost total control of the measurements, to fool the outlier detector with respect to this particular structure. So that's the key idea. And that's why I expect that even if there are more complicated situations where it's not as simple as that, like you don't only want to understand whether it's an anomaly, right? But you actually, or a stealth attack, but you actually want to understand if there is a particular underlying condition. So you have more labels. What I expect is that even if you cannot directly understanding with this simple threshold over this energy outside this subspace that you expect, then a neural network, a graph neural network, could possibly extract important features that are underlying that particular attack, not only to measurements, but possibly to the physical system, and provide the labeling. So really, wherever you think that filtering is an appropriate feature extraction step, then these ideas are really useful to understand how to do filtering for this type of signals, and therefore how to do a feature extraction for that. The simplest being, it shouldn't have this structure.
Yeah, very interesting. Yeah, it's very interesting. Yeah, it's very inspiring, actually. Oh, okay. Any other comments from the audience or question? Okay, very good. So just let me remind you that we also have Slack channels, and we have a Slack channel dedicated to this keynote. So in case there are additional comments or questions that you want to make to Anna, please feel free to use the Slack channel.
Yeah.
So Anna.
Yeah, also my email if anybody wants to email.
Yeah, Anna, thanks a lot. It was really nice having you with us today. And well, I think this concludes this session, the first keynote. It also concludes the first mirror from Europe. So maybe we can take a couple of minutes and then we can start with the opening of the second mirror. Okay, so just maybe a couple of minutes just to stop the recordings. Thanks, Anna.
Thank you. Bye-bye. Bye, everybody.